Hello, my name is Elizabeth Purser. We're going to be looking at the application called Sampling from a Finite Population. So what we're going to be doing is we're going to be approximating a sample proportion based off of a population. And in our example, we're going to be looking at the number of words with the letter E. So we're looking at a success or failure. We're randomly selecting from a population. And we need to follow the rule that the sample size must be at least 5% of the population to simulate the binomial distribution. So that's basically what the program is going to do, is it's going to estimate a binomial distribution. Just as long as, so we're repeating a sample, and as long as the sample is centered at the population parameter, then the sampling method is unbiased. And here's just a quick set of rules for each. So hypergeometric distributions must satisfy these. So we have to have at least 5% of the population. The sample size must be at least 5%. The trials are dependent, the trials without replacement, and we're also looking at specific values for hypergeometric. Whereas binomial, where we need the central limit theorem, each trial is identical and they're independent, and the probability of success is the same throughout each trial. Okay, so let's go right into the app. So we select Gettysburg, we go has E, we click this box. Okay. So let's try a sample. So we know in order for it to be a binomial distribution, it must satisfy the central limit theorem. And the central limit theorem basically tells us that the sample size, it's the sample size times the probability is greater than 10. And we know, because we're looking at a success or failure here, we're looking at yes or no. We're doing, what is it? Let's say n is equal to 10, and we're doing 10 times 0.5. So that's going to be 5, and 5 is less than 10. So the central limit theorem doesn't apply. But if we just draw the samples, we can see a distribution that's fairly normal. The standard deviation is 0.154 or 153, and keep note of that, because if we do a smaller sample size, and this is really small, so let's do 5, and look how the standard deviation it jumps, and that is because the smaller the standard deviation is, the closer the data is to the mean. So each trial with a sample size of 5, we're getting variant proportions. So they're varied, and the trials aren't really similar to each other. So let's try something that the sample size that satisfies the 5% of the population. So 5% of 268 is about 13. So when we do that, we get a standard deviation of 0.135, which is smaller. You can see it's smaller than 10. So we're getting values from each sample, we're getting data that's close to the mean and lower in variability. So it's going to give us a more normal curve. So let's see. So let's see something that sample size of 20, which applies for the central limit theorem, and it's also at least 5% of the population. So when we do a sample size of 20, you can see the standard deviation is really low, and we get this interesting curve. It's pretty tall, but the standard deviation is lower. So we're getting, basically all of our values are centered around the mean. So it might not be the greatest approximation. I would say looking at 13, it's kind of in between 20. So here's a summary of the data we calculated, or the standard deviations for each sample size. And as we see, 13 is kind of the middle ground. 20, we know that satisfies the central limit theorem, but when we looked at the curve, the values were centered around the mean. So it gave a normal distribution, but it wasn't as spread out as the sample size of 13. That was right on the dot.